Okay, so let's get started. Remember, we left out at this properties of determinants. We have mentioned already two properties of determinants. We said that if you switch two rows, the determinant changes sign, and if you multiply one row by a number, then the determinant also gets multiplied by the same number. So I will just try to summarize them. Let's say here on this frame. So properties of determinants. And so if we take A to be a matrix, so let A be a square matrix. Right? Otherwise, we can define determinant as square matrix. Okay. Then the first property, so switching two rows or columns changes the sign of determinant A, right? And the second one, if we multiplying a row or a column by a number k, okay, the determinant of A goes to k times the determinant of A. Okay, so in other words, the determinant itself gets multiplied by the same number. And I want to mention now the last property that I need for determinants, and namely, this is if you multiply a row and you add it to another row, which is, if you remember, the last operation that we defined on rows, then it turns out that this operation does not change the determinant of the matrix. So I will try to illustrate this on a concrete example of a 3x3 matrix. Not concrete, but a 3x3 matrix, although it's true for any square matrix. It could be 4x4, whatever size you take, okay? And the property is this. So if I take a matrix, so let's take the matrix, let's say, call it A. And the matrix has the entries, of course, A11, A12, A13, right? We have here A22, A21, sorry. A21, A22, A23, and then A31, A32, and A33. And let's now try to do the following. Suppose you multiply the second row by a number, and you add it to the first row, right? And we call this matrix, let's say, the transform matrix, let's call it B. And what is this matrix B? It's simply, it has, you see, the two rows in the bottom are the same, but the top row now has been changed into the first row plus some number times the second row. So it's A11 plus K times A21. And the second entry now is A12 plus K times A22. And the last entry here, it won't fit. So let me try to make some more room here. So it fits. Maybe I'll write it down here. So I will write it down here so there is more room for it. So the first entry in the first row is A11 plus K times A21. The second entry is A12 plus K, the same number K, of course, times A22. And the last entry of the top row is A13 plus K times A23. And of course, the remaining two rows are unchanged. So it's A21, A22, A23. And we have here A31, A32, and A33. And the claim is this. The claim is that determinant A is equal to determinant B. Okay? The determinant is unchanged. So this means that if you multiply a row and you add it to another row in a matrix, this does not change the determinant of the matrix. Okay? And to prove this, all I need to do is expand the determinant of B with respect to the top row. So let's try to expand it with respect to the top row. Okay? Remember, if we have a determinant, we can always expand it, right? And what's the expansion? So maybe I'll do it on a different frame. Okay, but we remember the entries. The entries are A11 plus K, A21, and then A12, and so on. Okay, so the determinant of B is going to be this. Okay, let me change the color. The determinant of B is going to be, so the first entry is what? The first entry is A11, right, plus K times A21, right, into the cofactor, which is C11, right, and plus A12 plus K times A22 into its cofactor, which is C12, plus A13 plus K into A23 into the cofactor, which is C13. And now let's expand now. So let me expand now the brackets here. So what do I get? And I will recollect. So I will recollect all the terms that contain K. I will put them on one side and separately. And the ones that do not contain K, we'll put them separately. So let me start with the ones that do not contain K. So it's A11 times C11 plus A12 times C12 plus A13 times C13, right? So these I will take them separately. Plus, then I have a common factor of K in every one of the remaining terms. So I have K into A21, C11 plus A22 times C12 plus, I will write it down here, plus A23 times C13. Okay, now I hope you can see what this is. Now, this is just the determinant of A, right? This one here is just the determinant of A. So, okay, so let me write it. So this is just determinant A, okay? So I can write here it's equal to determinant A, because you see it's A11 times C11. So it's the first entry of the matrix A times its cofactor. Plus the second entry here should be A12. This is A12 times its cofactor, and so on, right? So this is the expansion, if you like, of the determinant with respect to the first row of the matrix A. But what about this now? What about now this here term? And it turns out that this term is 0. Because this also looks like a determinant, right? If you try to expand it, you would get something like this. So this term here, I would write it down here. It is A21, A22, and A23. This is the top row. And then you see each cofactor now, C11. So this is obtained from, of course, removing a row and a column from the following, from A21, A22, A23. And this one here is A31, A32, and A33. Okay, because you see this C11, okay, is just this one here. This is C11, right? And C12 is what you get from these two terms here and these two here together. Okay? But now we know that this one is 0 since it has two identical rows. You see, it has two identical rows. The top rows are identical. So this determinant must vanish because this is the previous property. Remember when we said that we have two identical rows, we can switch them and they must change sign. But since they are identical, they don't change sign. And the only possibility that this may happen is when you have a 0 determinant. Okay? So in other words, all this is 0. Okay? And we are left with the determinant A. And as you see, determinant B is equal to determinant A. So if you multiply a row by any number you want, and then you add it to another one, this does not change the determinant of your matrix. And this is going to be very useful because by doing these transformations, you can always get the matrix into a simpler form in which you can easily calculate, or more or less easily, calculate the determinant of the its determinant of the matrix. I will try to illustrate this to you after I'm done with the properties. Do you have any questions so far? Okay, I need to mention just a few more properties. What if I multiply not a single row? Let's say I multiply two rows by, let's say by the same number or even by two different numbers. What will happen then? Then, as I know, every time I multiply a row by a number, the determinant will also get multiplied by the same number. So now if you multiply two rows by two different numbers, then the determinant will be multiplied by these two numbers. For example, if you multiply first, let's say the top row by 2, and then the bottom row by 3, then the determinant will get multiplied by 2 and then by 3, which means by 6. Okay? What would happen if I multiply the whole matrix by the same number? What do you think? If I multiply the whole matrix by the same number, what would happen to its determinant? So let's say, for example, you have a matrix which is 3 by 3. Okay? So A11, A12, A13, and we have A21, A22, and A23. We have A31, A32, and A33. And let's say now you multiply this matrix by a number, any number you want. Okay, let's call the new matrix B, and it is simply some number A, let's say, okay, A times A. Okay. So what will happen to the determinant of B? So how does the determinant of B, okay, relate to the determinant of A? So what can I say? So I need to remind you here that if you multiply a matrix by a number, then you have to multiply every row by the same number, right? Every entry, in fact, by the same number. And this means you are multiplying the first row, the second row, and the third row, right? And every time you multiply a row, the determinant will be multiplied by that number, right? So this means that the determinant of B is going to be A times A times A times determinant A. So it's going to be A cubed times the determinant of A. You see, there is a cube here because there are 3 rows. Yeah. If the matrix here A, let's say, was a 2 by 2 matrix, then you will get A squared. Because if you multiply the matrix by a number, then each row, and there are 2 of them, will get multiplied, and accordingly, the determinant will be multiplied twice by A times A. If you have a 4 by 4 matrix, then it's going to be A to the power 4. Okay, so remember that if you multiply one row, then the determinant will be multiplied once. If you multiply the whole matrix, then the determinant will be multiplied by the same number, okay, and the number of times is going to be just equal to the size of the matrix. So if it is a 3 by 3 matrix, then it's going to be multiplied 3 times, and so on. Any questions? Okay, then so the next topic is something that I already mentioned before. Determinant of A transpose is A transpose is the same as A. So transposing the matrix does not change its determinant. This is something that you need to keep in mind. And there is one more property which I think I skipped here, and this is something which is absolutely important, extremely important. I mean, you may forget everything I said so far. Of course, you shouldn't, but let's say you want to keep just one piece of information, it should be this. It should be this. I will just mention it without proof. If you have 2 matrices, 2 square matrices, and they are multiplied by each other, for example, 2 by 2 matrices or 3 by 3 matrices, okay, then it turns out that the determinant of AB is equal to determinant A times determinant B. Okay. So, can you hear me? Hello? Hello, can you hear me now?
Yes, doctor, we can hear you.
Yeah, okay, so this is my poor connection. Okay, now it updated. So you see, notice that the multiplication here between A and B is a matrix multiplication, while here it's just the ordinary multiplication of 2 numbers, because determinant A is a number and determinant B is a number. So here we are multiplying simply determinant A by determinant B. So for example, let's say I have two matrices A and B of the same size, let's say 3 by 3 or 4 by 4. Okay? One has determinant, suppose 5, and the other one has determinant 3. Then what will be the determinant of the product, A by B? And it turns out that this is always true. The determinant of A times B matrix multiplication is equal to the determinant of A times the determinant of B. So it will be 5 times 3, which is 15. This is a general rule. I mean, this is one of the most important properties of determinants. In fact, the determinant is defined the way it is because of this property to make it true. And from here, we can now deduce the determinant of the inverse matrix, and this will be our last property that I would like you to remember about determinants. Okay, so I remind you that a matrix A has an inverse such that A inverse equal to A inverse A, right, equals to the identity. By the way, what will be the determinant of the identity? The determinant of I. Okay. So let's remember, what is the identity? The identity is just the matrix which has ones on the diagonals, right? So let's say it's a 3 by 3, so 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. So what is determinant I? Let's try to find it. Okay. So how do I do it? How do I do it? I need to pick a row. Let's pick the first row, right? Pick the first row and expand, right? So I will get 1, right, times its cofactor, and the cofactor is -1 to the power 1 plus 1, right, into the minor, and the minor is the determinant of this matrix, the determinant of this matrix down here, right, and this is obviously 1, right, plus, now you see I don't have to expand with respect to the rest because here I have 0 and here I have 0, so whatever the cofactors, they are going to contribute nothing, just zeros, right? So that's it. It's just one term in the determinant, okay, one term, and obviously it's equal to 1. So the determinant of the identity is just the number 1, and this is true for any identity, no matter what size it may be, 2 by 2, 3 by 3, 4 by 4, whatever. Okay, and now we apply this rule. Now we apply the rule that we introduced here, that if I have a product of two matrices, then the determinant of the product has to be equal to the product of the determinants. Okay? So I'm going to do it here. I will apply it to this one here, right? And this tells me that determinant of A inverse A, okay, must be equal to the determinant of A inverse times the determinant of A, right? But on the left-hand side, I can replace A inverse A. I can replace it by the identity. So it is just the determinant of the identity must be equal to the determinant of A inverse, right, times the determinant of A. But this left-hand side is just equal to 1. We have just seen it. If I have the identity, the determinant is 1, right? And this implies that, you see, the determinant of the inverse matrix, this is equal to
1 over determinant
is equal to 1 over the determinant of A. Okay. So if I give you a matrix A and I ask you what is the determinant of its inverse, all you have to do is find its determinant and then divide 1 by that determinant, take the reciprocal of this. Okay, so now I will try to illustrate all this to you. Okay? I will try to illustrate all these properties on a very simple example before we move on to applications. And in fact, there will be only 1 or 2 applications on determinants because of the time constraint. Do you have any questions before I move on to examples? No question? Okay. Then let's take an example. I think last time we had some nice examples. Let me just remember we had, no, not here, just a minute. We had this matrix where we needed to calculate the determinant, and it was really a big one. The solution to to assignment number 9. So we had here a big determinant. I think it was this one. I think so. I will take this matrix, okay, as our example. So I will call it matrix A, and this is the matrix A. It's 1, 3, 2. I will just copy it. 1, 2, 3, 1, 1, 2. Okay, and now I'll go back to share this with you so you can see it. Okay, properties of determinants, and let me go to the last frame. See, okay. So here's a matrix A. Okay, I want to find its determinant, and of course you can do it. I mean, straightforwardly. You can pick a row and try to expand with respect to this row. Okay, but remember that you can always try to simplify it using the properties that we have already mentioned. For example, you can switch two rows, right? You can multiply a row by a number, and you can multiply a row by a number and add it to another row. So what I'm going to do now is to try. So I want to. The question is calculate determinant A. So this is my question. Calculate what is determinant A. Okay, and in order to find this, I'm not going to use A. I'm going to somehow manipulate A little bit. Okay, and get a nicer matrix for which I can find the determinant much more easily. Okay? So I will do now this transformation. I will go from A, okay, and I'm going to, so remember, whenever you want to calculate a determinant, right, it's good to have zeros in the rows about which you are going to expand. For example, if you choose to expand about the first row, then let's try to make as many zeros as possible in the first row. Okay? And the thing I'm going to do is, look, I'm going to take the last row, multiply it by -1, okay, and add it to the first row and replace the first row. And I will tell you why, okay? Because if I do this, look what happens now. If I do this, then I will get a new matrix, okay? And you see now the 1 here will become a 0, right? This 3 will become a 2, and this 2 will become a 0, right? And of course, the rest will stay the same. 1, 2, 3, 1, 1, 2. Now, I know that this property does not change the determinant because we have just seen it, right? If you multiply a row by a number, you add it to another row, the determinant stays unchanged. But what have we achieved? Oh, we have achieved a lot, because now, instead of having now 3 numbers here in the first row, right, you have now 2 of them zeros, right? This 0 here and this 0 here. And this means that you don't have to calculate the cofactors. You just have to calculate the cofactor of this number, right? And multiply it by the number, and this is going to be the determinant. So what is the determinant of A? Determinant of A is going to be, right? It's going to be 2 times -1 to the power 2 plus 1, right? Times the minor, right? What is the minor? So remember, we need to remove the second column and the first row. This is the minor 1, 3, 1, 2, right? And what is this? So this is 2 times -1 to the power 3. So it's -1 times 2. It's -2 into 1 times 2 minus 1 times 3. So it's -1 and -2. So it's 2. Just that's it. The determinant is 2. Yeah, much easier, right? Much easier than doing what we did before. I will try to show you what we did before. Can I do it? I will try to duplicate this so I can switch between the two, right? Yeah, I think I can. So I will show you what we did before to calculate that determinant. It was really a long calculation, right? It was really long. That's it here. You see, we got here. So we wanted to find this determinant. Here it is. You see, here it is. Here down here, right? And we found it to be 2. But look what we did. A lot of calculations, right? Now we all did it in one line, right? We just transformed the matrix, manipulated the rows, so that now we can easily calculate the determinant. Isn't this nice? Can you hear me? Hello, can you hear me?
Yes, doctor.
Okay.
Yes, doctor.
So I hope you got the idea, right? So the idea is just to manipulate the rows a little bit so as to make as many zeros as possible in a given row, and then expand with respect to that row. This will make your life much easier, okay? And let me see now what happens if I multiply, let's say, suppose, let's say the top row, I multiply it, so the determinant of A is equal to 2, right? So what if I multiply now the top row by 2, okay? Let's say I multiply the top row by 2, what's going to be the determinant of the new matrix, okay? So let's say now I'm going to copy it first and then show it to you. So A was this matrix, 1, 3, 2, 1, 2, 3, 1, 1, 2. And now I'm considering this matrix where the first row has been multiplied, I said by 2 or by 3, let me multiply it by 3. So it's 3, 9, 4, okay? And the rest is the same. Okay. So here's the matrix. You see, if you compare A to B, you can see that they have in the bottom two rows they have the same entries, but in the first row, in the top row, the entries have been tripled, right? So instead of 1, I have 3. Instead of 3, I have 9, and instead of 2, I should have 6. Sorry, it's my mistake. It should be 6 here. Okay, and the question is, I know that determinant A is equal to 2. We have just found it, okay? The question is, what is determinant B?
3
Okay,
times.
now define, yeah?
3 times 2.
Yeah, it is just 3 times 2, right? We can use this property that if you multiply the one of the rows of a matrix by a number, then the determinant gets multiplied by the same number. So it's going to be just 3 times the determinant of A, right? Which is 2. So it's 3 times 2, which is 6. Now we can just, of course, now this is true. And if you are to calculate this, I mean, the easiest way is to apply this property, right? But just to check it, right? So what should I do now to calculate? If I want to calculate the determinant of B, straightforwardly, right? Then I need to pick a row and expand, right? And let me do it now with respect to the first row. But first, I'm going to make more zeros, right? So what I'm going to do now in B, okay, I'm going to multiply the bottom row, right, by -3, right? Yeah, and add it to the first row and place it, of course, in the first row. Then what would happen now to the matrix B? Of course, this would become a 0, right? This would become a 6, right? And this would become a 0, okay? Because 3 times 2 is 2, and 6 minus this would be 0, and the rest will stay unchanged. Okay, and I want to find the determinant of this. So what is the determinant of this? I want to find the determinant. Okay? And all I need to do now is expand with respect to the top row, but I have only one non-zero entry, right? This one. So I need to calculate its cofactor and multiply it by this entry. So it will be 6 times -1 to the power 2 plus 1, right? Because it's the first row and the second column, times the minor, which I get after I remove the second column and the top row. So it will be 1, 3, 1, 2, right? And if you do it, you will get exactly the 6. Okay? You see, this way is much easier, of course. Once you know the determinant of A, using this property makes your life much easier, much easier. Okay. If I ask you to calculate the determinant of A transpose, what is the determinant of A transpose? So again, the determinant of A transpose. Okay, what is this? By the property, it's going to be just the determinant of A. There will be no difference between the two, and this is going to be just 2, what we have found, right? And similarly, if I ask you to find determinant of A inverse, you don't have to find the inverse matrix and then find its determinant. You just use a property, it's 1 over determinant A, okay? And this is going to be, of course, 1 over 2, right? So it's just, now, of course, here I need to mention that you see the determinant of the inverse is defined only when determinant A is not equal to 0, right? The determinant of A is not equal to 0, okay? And this tells you that the matrix A will admit an inverse only if the determinant of the matrix is not equal to 0. And this is something that I want you to remember, Okay, so this is one property also. Remember, I told you how to calculate the inverse using the augmented matrix, right? But I did not tell you whether there is an inverse or not. And now it turns out there is a very nice way to check whether a given matrix has an inverse. So if you want to check the existence of an inverse, okay, you don't have to start directly by calculating the inverse. You calculate its determinant. So, okay, so let me write here checking if A admits an inverse. Okay, how do you check? Okay, what do you do now? You don't directly augment the matrix by the unit matrix and try to manipulate the rows into the row echelon form or reduced row echelon form. What you do is calculate determinant A. Okay, so if determinant A is not equal to 0, then A inverse exists. Okay. Otherwise, if determinant A is equal to 0, right, then A inverse does not exist. That's it. Because it can't be, right? I mean, there can't be a matrix which is the inverse of A, okay, when the determinant of A is equal to 0. Because in that case, according to this property, so let me take you back to this property, right? If the determinant of A is equal to 0 and the inverse matrix did exist, right, then the determinant of that inverse matrix would be 1 over 0, which is infinite, right? 1 over 0 is undetermined, it's undefined, right? So you cannot do it, right? So it can't be the case. It can't be that the determinant of A is equal to 0 and the inverse matrix exists. Right? So in other words, if you want to check whether the inverse matrix exists for any given matrix, you begin by calculating its determinant. If the determinant is equal to 0, there is no inverse. If it's different from 0, there is an inverse. Okay? Questions? Okay, I think we are done with the properties. Let me just check here whether the book is mentioning any other properties. No. Okay, yeah, that's it.